Welcome you all again for the Thermodynamics lecture series. Today we are going to discuss about some problems on first law of thermodynamics. So in this lecture I am going to solve a problem on first law of thermodynamics. Problem 6. A fluid is confined in a cylinder by a spring-loaded frictionless piston so that the pressure in the fluid is a linear function of the volume P is equal to A plus BV. The internal energy of the fluid is given by the following equation: U is equal to 34 plus 3.15 PV, where U is kilojoule and pressure P is in kilopascal and volume V is in meter cube. If the fluid changes from the initial state of 170 kilopascal and 0.073 meter cube of volume to a final state of the final pressure of 400 kilopascal and the final volume of 0.06 meter cube with no other work that done on the piston. Find the direction and magnitude of the work and heat transfer. So in this problem you consider a cylinder. Okay, so in the cylinder is filled with the fluid. Okay, that is the fluid is compressed by using a compressed or expansion by using a spring loaded frictionless piston. Okay, so that the pressure in the fluid can be increased or decreased by adding weight on the frictionless spring loaded frictionless piston. Okay, so by using this a linear function, that is pressure, by varying the pressure, where here they are using the linear function P is equal to A plus BV. This volume V is in meter cube and A and B are constant and P is pressure. Then the internal energy is denoted by the equation U is equal to 34 plus 3.15 P into V, where this U is in kilojoule and this P, pressure P in kilopascal, and this volume is meter cube. So you have to check whether the unit of the volume is in meter cube or meter cube per kg. If in the question, if it is given as meter cube per kg, you should have to written this as small v as specific volume. But in this case, the question itself they have mentioned clearly it is meter cube, so it is volume, total volume, then it is given. If the fluid changes from initial state, that is initial state is denoted as 1 and final state is denoted as 2. So initial state of kilopascal, so it is pressure. So P1 is 170 kilopascal and volume V1 is 0.03 meter cube, and the final state is denoted as 2. So pressure P2 is 400 kilopascal and volume V2 is 0.06 meter cube. So with that we need to find it out the work and the heat transfer, and also we need to check the sign of the work and heat transfer, and we have to infer whether the heat is transferred into the system or transferred out of the system, and the work is . So I am writing this U1. So U1, in the question itself U1 is given. U1 is equal to 34 plus 3.15 into PV. Okay, for U1 I am writing for the initial condition 34 plus 3.15 plus pressure P1 is 170 and V1 is 0.03. By solving this equation, what you can get, U1 is equal to 50.065 kilojoule. In the similar way, I am substituting the second state values, that is U2 is equal to 34 plus 315 P2 V2. So P2, from the question P2 is 400 kilopascal and V2 is 0.06 meter cube. Substitute these values, you will get U2 is equal to 109.6 kilojoule. So we know that the delta U is the difference between their internal energy. So we can write delta U is equal to U2 minus U1. Because in the first law of thermodynamics we can write Q is equal to W plus del U. So we need to find it out del U. So del U is U2 minus U1. So U2 is 109.6 and U1 is 50.065. So these two are in the same units. So we can substitute as it is. So delta U is equal to 109.6 minus 50.065. You can get the change in internal energy. Delta U is 59.54 kilojoule. And also the another one relation is given, that is linear function is given. P is equal to A plus BV. This A and B are constant. This P is pressure and B is volume. So as I said earlier, we need to find out these two constants of A and B. How we can find? By applying the initial state, I can rewrite this equation as P1 is equal to A plus B into V1. So P1 is given in the question, so it is 170 kilopascal equal to A plus 0.03 is your volume, total volume of the initial state in meter cube. So we substitute V1 is equal to 0.03 of B. So this is one linear equation. You can find it out. This is linear equation, and you substitute the values of the final state in this equation. You can get P2 is equal to A plus B into P2. So from the given data, P2 is 400 kilopascal, which is equal to A plus 0.06 into E. So this 0.06 is final volume of V2, that is 0.06 of meter cube. By solving this two linear equations, you can obtain A and B. Okay, by solving these two simple equations. Okay, by linear solving, by these two simple equations, you will get A is equal to minus 60 and B is equal to 7666.67. Okay, I am substituting these constant values in this first equation. Okay, what I can get, P is equal to minus 60 plus 7666.67 V. Okay, so this A is minus 60 and B is 7666.67 V. Further, we know that work done is equal to integral of P into dV, where this P is pressure and dV is change in volume. So this integral represents this initial state to final state. So in the previous one, we have found out the pressure equation, that is P is given as the linear function P is given as A plus BV, and also we have found out the constant values of A, that is minus 60, and B is 7666.67. So P is equal to A plus BV. So that term you have to write it out. Then V into dV. Okay, when integrating this, what you can get, these are all the constant values. When we integrate of V into dV, what you get, V square by 2. Okay, when you integrate x into dx, what you get, x power n plus 1 divided by n plus 1. In the same way, V into dV. Okay, so this V into dV, when integrate V into dV, what you can get, V power n plus 1, that is 1 plus 1 divided by 1 plus 1 2, so that is V square by 2. And we have to write lower limits to upper limit. So lower limit, here we are changing the variable as volume, so we have to write change into V1 to V2. Okay, so that is minus 60V plus 7666.67 V square by 2, the lower limit of V1 and upper limit of V2. So we know that the V1 is 0.03 and V2 is 0.06 as given in the question. Okay, you substitute the limits here. What you can write, that is 1 to 2. The limits is 1 to 2. So you substitute minus 60, V2 minus V1, upper limit minus lower limit, and also 7666.67 divided by 2. Take these values, and also V2 square, that is V2 square minus V1 square. Okay. By substituting these values, here V2 is also 0.06 and V1 is also 0.03. By solving this equation, what you can get, work done is equal to 8.55 kilojoule. Here work done is positive. Okay, when the work is taken out of the system, so the work is done by the system. That is the magnitude. Then we need to find it out Q, the net heat transfer. Q is equal to W plus del U. According to the first law of thermodynamics, Q is equal to W plus del U. So we know W, so from here we know W, and in the previous we find it out internal energy, change in internal energy delta U, U2 minus U1. By adding those two values, that is Q is equal to W plus del U, you can get Q is equal to 68.085 kilojoule. Here Q is also plus, so Q is also in the sign convention. You check the sign convention, Q is in positive, the heat is transferred into the system. Whether the heat is taken out of the system, it is negative. Here you comparing these two. Okay, these two was in positive cases. Here in this case, the work is taken out of the system and the heat is transferred into the system. Okay, so it satisfies your first law. When the heat is given into the system, we can take work output in this problem. Okay, so the heat is given into the system, the heat is transferred into the system, so it is positive, and here the work is taken out of the system. So the net work transfer is 8.55 kilojoule and your net heat transfer is 68.085 kilojoule. Heat is transferred into the system. Thank you.